The group of elements known as the lanthanide series lies at the very bottom of the periodic table. The lanthanides share some properties with the transition metals, including high melting and boiling points. They also react easily with oxygen and water and dissolve in acids. Although they are a subseries of the transition metals, the series is usually considered a separate group. The group typically includes the 15 elements from lanthanum to lutetium. Most lanthanides have a shiny silvery or pale gold appearance and are all solid at room temperature. The lanthanides are commonly used for specialized lighting, lasers, and magnetic applications. They are also called the rare earth metals because when they were discovered, they were very difficult to isolate, so scientists thought they were uncommon. In fact, the elements in the lanthanide series are quite common. The only lanthanide not found on Earth is promethium. All of its isotopes are radioactive, so any promethium that may have existed on Earth at one time has decayed into other elements. The lanthanides are difficult to isolate because they closely resemble each other at the chemical level. This similarity is due to their electron configurations, which can be explained by a close look at the periodic table. The elements are listed in order of their atomic number, which represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is also surrounded by an equal number of electrons. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. The lanthanide series is entirely in period 6, since every atom has 6 electron shells. The electrons in this outermost shell are called valence electrons. It takes 8 valence electrons to fill an outermost electron shell and make an atom stable. For most groups on the periodic table, the number of valence electrons an element has corresponds to its position on the table. For instance, sodium in group 1 has 1 valence electron, and calcium in group 2 has 2 valence electrons. But the lanthanide series is different. Each lanthanide has 2 valence electrons in the s orbital of its 6th level shell. But some also have a free electron in an interior d orbital of their 5th level shell. And as the atomic number of the lanthanides increases, additional electrons are added to another interior orbital, the f orbital in the 4th level shell. Each orbital in an atom is made up of suborbitals, which can hold 2 electrons each. The number of suborbitals determines the number of total electrons in an orbital. The s orbital is made up of a single suborbital, so the maximum number of electrons it can hold is 2. At the other extreme, the f orbital consists of 7 sets of suborbitals, so it can contain a total of 14 electrons. Just as atoms are most stable with 8 electrons, suborbitals are most stable with 2 electrons. To make the most stable atom, electrons in certain lanthanides jump between the f and d orbitals. The lanthanides are so similar because as an atomic number increases, electrons are added to the innermost f orbital instead of the valence shell. This minimizes any effect the additional electrons have on the properties of the element. Because they are similar, lanthanides need not be isolated to be useful. One of the most common uses for the lanthanides is mish metal, a metal mixture used in steel production, magnetic alloys, and vacuum tubes. It is approximately 50% cerium, 25% lanthanum, and 25% other lanthanides.